Okay, so part 3 of chapter 3 is the kinetic model of an ideal gas. Okay. 3.2.9 is just defining pressure. So this should be familiar, the student should be familiar with this. Pressure is the force over area. However, you want to tell them how this pressure is exerted on the walls of a container by a gas. So what happens is that the gas particles or the gas molecules, they collide with the container of the gas and then they change direction. So when they change direction, that means there is a change in momentum. Okay? A change in momentum indicates that an external force was applied on the particles. By Newton's third law, we know that if there was an external force applied on the particles also exerted a force on the walls of the container. So this force divided by the surface area of the container gives you the pressure exerted on the walls of the container. Okay? So 3.2.10, this part gives you 6 basic assumptions of the kinetic model of an ideal gas. So basically simplifying an ideal gas, simplifying solutions by talking about ideal gases. And for an ideal gas, we have these 6 assumptions. So the most important assumption out of this is that there are no intermolecular forces between the molecules of an ideal gas. Now the other assumptions are important as well, but this is key for understanding some of the behaviors of an ideal gas. For example, as we talked in the previous part, how internal energy is a direct has a direct correlation to temperature in an ideal gas. Alright, so that's 3.2.10. The next part is state that temperature is a measure of the average random kinetic energy of the molecules of an ideal gas. We've already talked about this, that how the temperature is related to the average random Ke. It just goes into a little more detail over here. There is a very detailed or very elaborate explanation of this. It's not in their syllabus, but it's online. Sometimes it helps if the student is a little more curious. You can probably fetch it from Wikipedia or any source online and get a derivation of how the average random kinetic energy of each particle is related to the temperature. This here is the temperature, and K here is a constant called the Boltzmann constant. Okay? So if the student is more of the inquisitive type, you can probably go and get a derivation of this. But the key takeaway from this is that the temperature is directly related to the average random kinetic energy of the particles. Now the next portion here shows you the Maxwell-Boltzmann speed distribution curves. I'm not going to draw it out here, but basically in this portion the students need to identify the shapes of the Boltzmann curves and know that the peak of the curve, the salient features of the curve. Firstly, the curve is tilted a bit to the left. It's a curve of the number of particles, the relative number of particles with the speed of each particle. Okay, so the curve is slightly skewed to the left. Okay, and it never reaches the x-axis here. Why? Because there is always a certain number of molecules which have very high speeds. Okay, as you increase the temperature, the curve gets shorter. Okay, and it gets more symmetric. Okay, so this is for temperature T1, which is a temperature less than T2 and which is less than T3. Okay, so T3 is greater than T2, greater than T1. Okay, so the velocity of the particle, generally the number of particles with higher velocity increases, as you can see, with an increasing temperature. Okay, another salient feature of this curve is that the peak of the curve at any particular temperature is called the most probable speed, okay, VMP. This is the velocity at which most of the particles are likely to be at. Alright? Now also make sure that the students understand that the area under this curve remains the same for the same gas. Alright? Now the next curve here is the distribution. This curve has a name. It's called the Maxwell-Boltzmann speed distribution curve. This is different from the distribution of kinetic energies. Okay? So the distribution of kinetic energies looks similar. The curve shapes are similar, except that we have instead of speeds on the x-axis we have kinetic energy. Okay? So again, for the same gas at a higher temperature, you will have a flatter curve, okay, where this is T1 and this is T2. Okay. Note that at the same temperature, this is important, at the same temperature the average random KE of the particles of all gases is the same, but the speed distribution curve may not be the same. For example, hydrogen gas and oxygen gas at the same temperature. Okay, the average random KE of the particles is the same, but that does not mean that the speed of the particles is the same. Why? Because hydrogen molecules are about 1/16 the size in mass of the oxygen particles. Therefore, the hydrogen particles would be at a much higher speed for the same temperature. So their Maxwell-Boltzmann speed distribution curves would look different. Okay? That's the second portion. Now the last part of this one is 3.2.12. Explain the macroscopic behavior of an ideal gas in terms of a molecular model. Okay. So this portion here is basically talking about how we arrive at the ideal gas equation. What I like to do is because in your notes here you start off with Boyle's law. Again, this is very theoretical, the explanation of the laws. The students do not actually need to get into too much detail over here, because it has hardly ever been that they've been tested directly on what is Boyle's law or what is Charles' law and the pressure law. Okay? What you can do, they may not even be expected to know these individually. What's most important is that they understand the ideal gas equation. From Boyle's law, we understood that pressure is inversely proportional to volume. So therefore, two states of pressure and volume, the multiplication of them would be the same. It would be constant for the same gas. And this holds true at a constant temperature. Okay? Charles' law states that the volume of a gas is directly proportional to its temperature in Kelvin. Okay? So that's important. You wanna know. You wanna make sure that they understand that this temperature here is the absolute temperature in Kelvin. Therefore, for two states of a gas, V1 over T1 would be equal to V2 over T2. Okay? And this here is for a fixed mass of gas and at a constant temperature, at a constant pressure. Okay? Pressure law states that the pressure of a gas, a fixed volume of gas, pressure of a fixed volume of gas is proportional to its temperature. Therefore, for two states, P1 over T1 would be equal to P2 over T2. Okay, this is at constant volume. Okay, so these are the three laws, and a summation of all these three laws arrives at the ideal gas equation, which states that the pressure multiplied by the volume of an ideal gas is equal to the number of moles multiplied by R, which is a universal gas constant, okay, multiplied by the temperature. So PV equals nRT. They should be familiar with this. So an ideal gas is defined as a gas which obeys the ideal gas equation for all temperatures and pressures. Okay. Now real gases obey the ideal gas equation under circumstances where they are pretty much like ideal gases. Those are conditions of low pressure, okay, because at low pressure the molecules are further apart, and therefore the intermolecular force of attraction don't come into play. Therefore real gases behave like ideal gases at low pressure and or high temperature. Okay, so at low pressure and high temperature real gases would follow this, but an ideal gas is a gas which obeys this equation at all temperatures and pressures. You can see that this equation allows the students to figure out all these three relationships. For example, at constant temperature, this entire portion here becomes constant, and therefore P multiplied by V becomes constant. Similarly, at a constant pressure, P is constant, N and R are all constant, therefore volume is directly proportional to temperature, and so on and so forth. So the students basically need to understand this. The continuation of this and an elaboration on ideal gas happens in the HL portion of thermal physics. And that's the end of chapter 3.